Okay, so again, good afternoon. Our topic for this afternoon is about the PN junction. So we will start with the structure of PN junction, starting from the N-type, then P-type, then structure of PN junction, and we will give examples of PN junction. So again, I'm Sir Febus from the School of Electrical, Electronics, and Computer Engineering of Mapua University. So again, the N-type semiconductor is an extrinsic semiconductor with more negative free electrons than positive holes. So that is the main reason we describe this extrinsic semiconductor as negative type. So free electrons are the majority charge carriers. So that means there are more number of free electrons. So that's why they are referred as majority carriers. While holes are the minority charge carriers. So for the N-type, we have here an illustration showing a silicon mixed with phosphorus. So phosphorus is an example of pentavalent dopant where it will donate an extra free electron without any hole pair. So if there are 10 million phosphorus dopants, then there we will have 10 million free electrons without any hole pair. Okay? So regarding this structure, the most important part would be the excess free electron from the pentavalent dopant. So if we remove a negative electron to the material, the remaining material will become positively charged. Tama ba? So pag inalisa mo ng negative electron, the remaining material would become positively charged. So the N-type will now behave like a positive ion. So sineperate lang natin. No? You have the excess free electron from the pentavalent dopant. And when we isolate this, the remaining material will have a positive charge after removing the negative excess free electron. So the remaining material can be represented with a positive ion. So the N-type can now be simplified. No? So instead of using this type of drawing, we can draw N-type using this. Just present or draw or illustrate a free electron paired with a positive ion. Okay, is this clear?
Yes po, sir.
All right, thank you. So whenever I draw this, I am representing an N-type material, no? A free electron paired with a positive ion. Now for the P-type, P-type is an extrinsic semiconductor with more holes, with more positive holes than negative free electrons. So that makes it a positive type material. So holes are the so-called majority charge carriers, while free electrons in P-type are the minority charge carriers. So for our P-type, we can illustrate using silicon atoms in a crystal mixed with boron atom. So boron is an example of trivalent atom. So when it connects or bonds with other neighboring silicon atoms, it will leave a vacant space. So that would produce a hole, an extra hole without any free electron hole pair. So from this structure, we can isolate the hole. So you have an excess hole from every trivalent dopant. Then the remaining material can be represented by a negative ion. So the remaining material will have a negative charge after removing the positive excess hole. So the P-type material can now be represented by a hole paired with a negative ion. Okay? So we can draw a p-type material using hole represented by letter H paired with negative ion. So every boron dopant, pag meron kang boron dopant dun sa crystal material, you can draw this kind of representation. Okay? Again, is this clear?
Yes, sir.
Right, thank you. So we'll continue. Now, for the PN junction to build a PN junction, we can fabricate a p-type on one side. So notice that the p-type side has holes paired with negative ions. And the other side, we can fabricate the n-type side, represented by free electrons with positive ions. The boundary where the p-type and n-type material meets, that is what we refer as the junction. So this is the area where the p-type meets with the n-type. Okay? So yun yung pinaka-boundary natin. For ideal representation, we can clearly show the PN junction. So ito, ang tawag natin dito is step junction. No? Immediately from p-type, after the junction, it automatically becomes n-type. But for practical device, it is not actually a step junction, but rather it is a gradient junction or gradual junction. It means that the concentration changes gradually. So you have pure p-type, and then pag meron kang junction, yung p-type concentration bababa, and then you have a bit of neutral material, then low concentration n-type, and then you have high concentration n-type. So yun yung actual, no? Gradual talaga yung junction. But normally in electronics, when we present the junction, normally it is a step junction. Okay? Kumbaga, from p-type, automatic magiging n-type siya. Okay? And when we say PN junction, again, this is the area in semiconductor devices like diodes and transistors. This is the area connecting the p-type and the n-type materials. So p-type side has holes and negative ions, while the n-type side has free electrons and positive ions. Now, regarding the concentration of carriers in PN junction, on the p-type side, we can denote the concentration of holes in p-type side as P sub P. So P is the concentration of holes, and then sub P indicates it is on the p-type side. And we can denote the concentration of electrons in the p-type side as N sub P. So N is the concentration of electrons, and sub P means we are referring on the p-type side. And for the p-type side, the concentration of holes is determined by the doping concentration of p-type material. So this is the acceptor doping concentration, while the concentration of electrons on the p-type side can be calculated using this equation. You have Ni squared over the acceptor concentration. While on the n-type side, we can denote the concentration of electrons in n-type side as N sub N, while the concentration of holes in the n-type side can be denoted as P sub N. So N sub N is defined by the concentration of donor atoms, while the concentration of holes in the n-type side can be computed using the Ni squared over the donor concentration. Okay? So is this clear so far?
Yes po, sir.
All right, thank you. And we have here examples of PN junction. So again, PN junction is the boundary between the N-type and P-type materials. And one example is a diode device having one PN junction. This is the cross-section of a diode. You have a P substrate, and inside the P substrate, so this is actually the silicon wafer. So inside the silicon wafer, we fabricate a large N-type layer referred as a well. So you have a large N-type area, and we call it well. And inside the well, we will fabricate the P-type. So the contact cuts connecting to the N well will serve as the cathode terminal, while the contact cuts connecting on the internal P-type will serve as the anode terminal. So you have the PN junction between the anode and the cathode. So this PN junction is the PN junction of our diode. But actually, if we look at the cross-section, there is another PN junction between the diode. So this is the diode itself, the P-type and the N-well. So between the silicon die, there is another PN junction between the diode and the substrate. So we will just consider the PN junction between the anode and the cathode. So to represent a diode, we can just pick up the P-type to connect to anode and the N-well or N-type connected to the cathode. All right, so this will now show a single PN junction. So this kind of structure can represent a semiconductor device or a semiconductor diode. So notice that P-type is labeled as the anode terminal, while the N-type side is labeled as the cathode terminal. So this will be the anode-cathode PN junction. And in terms of schematic symbol, circuit symbol, this is how we draw the symbol for a diode. So this side is the anode, and the other side with the negative sign that will indicate the cathode terminal. And in schematic diagram, we normally label diode using letter D. Obviously, D means diode. No? And another example of PN junction, we can find two PN junctions in NPN bipolar transistor. So here is a cross-section of the NPN bipolar transistor. So from the silicon wafer or the P substrate, you have a large N-well connected to the contact cut serving as the collector terminal. Inside the N-well, you have a P-type region connected as the base terminal. And inside the P-type, we have the N+, indicating a high concentration N-type. So with the contact cut, that will serve as the emitter terminal. So you have the PN junction between base and emitter, and another PN junction between the base and collector. So the N+, P-type, and the N-well comprise the NPN bipolar transistor. And in the cross-section, again, we have additional PN junction between the transistor and the P substrate. Now, to simplify the drawing, we can just represent the N+ for the emitter, P-type for the base, and N-well or N-type for the collector. So you can have here again N+ as the emitter, P-type as base, and N-type as the collector. So from here, you have the base emitter PN junction, as well as the base collector PN junction. So bipolar transistor has two PN junctions. Then in terms of schematic diagram, this is how we draw the symbol for the bipolar transistor. Okay? So the arrow indicates the emitter terminal. The middle terminal is the base, and the other one will be the collector. Okay, can you follow? Please confirm.
Yes, po, sir.
All right, thank you. So that ends our discussion on the structure of PN junction. So let's continue on the PN junction in equilibrium. So what happens, what is happening inside the PN junction when there is equilibrium? So when we say equilibrium, there is no movement of carriers. Okay, so the carriers are assumed to be in their location. So they are not moving Therefore, there is no electrical current. Okay. So inside this slide, we will know the PN junction without bias, what is the diffusion, what is recombination, depletion region, built-in potential, and the barrier potential. Okay, so let us start. So again, this is the PN junction, which is the physical boundary between P-type and N-type layers. And note that the operation of semiconductor devices depends on the condition of PN junction. The semiconductor device will conduct current when the PN junction has low resistance. So we can control the internal resistance. Okay? So we can make the resistance of PN junction to become lower, or we can also make it higher by applying external voltage. So ganun yung operation natin. No? So semiconductor device conducts current when the internal resistance of PN junction becomes lower. And the semiconductor device will prevent current when the PN junction has high resistance. So we can say that the resistance of PN junction in semiconductor devices like diodes and transistors, the resistance changes according to the applied voltage. Or sa electronics, we call it as bias voltage, biasing voltage. So here is the biasing of PN junction. So biasing means the application of DC voltage with appropriate polarity to the PN junction. Okay, so biasing is the application of voltage with appropriate polarity. So that is the concept of biasing. In ordinary meaning, when you say bias, it means merong preferential treatment. Merong kang predetermined selection. Yun yung bias natin. So that comes in on the polarity. So we do not just apply voltage, but you have to select where to connect the positive terminal, where to connect the negative voltage. For example, in our remote control in television, sa TV natin, when the battery becomes low bat, we change the battery and we do not just insert the battery, no? You have to be aware where to connect the positive and where to connect the negative. Since the remote control has semiconductor devices, they require proper polarity. So the voltage must be properly selected in terms of the polarity. So yun yung ibig sabihin ng bias natin. Is that clear?
Yes, sir.
Okay, thank you. So I'll continue. So the first type of biasing is what we call forward bias. This is the biasing condition wherein the PN junction has low resistance and conducts current. The other type of biasing is the reverse bias. This is the biasing condition wherein the PN junction has high resistance and prevents current. Or sometimes we say, when it is forward bias, the device is turned on. When it is applied with reverse bias, the device is turned off. So minsan ganun yung description natin. But before continuing with the forward bias and the reverse bias, let's start with the PN junction without bias. What is happening inside the PN junction when there is no applied voltage? The first possible scenario is there is a probability of diffusion process. So when you say diffusion, even without applied voltage, charge carriers move across the PN junction from area of higher concentration to region of lower carrier concentration. So from our previous lecture, we discussed the diffusion current. This is the movement of carriers due to concentration gradient. So from the p-type side, you have a high concentration of holes. And on the n-type side, there are no holes. So the natural tendency is for the holes to move towards the n-type. Likewise, in the n-type side, you have high concentration of free electrons. While on the p-type, we don't have any free electrons. So the natural operation is for the free electrons to diffuse or to move towards the low concentration p-type. Okay? So the first possibility is the process of diffusion. So electrons will diffuse from n-type going to the p-type, while holes will diffuse or flow from p-type going to the n-type. So that will provide the diffusion current. Okay? So dependent on the concentration gradient. Now, after the diffusion, as the electron, so let us focus our attention on the electrons. So let's say the free electrons diffuses across the p-n junction. Then when the free electrons are nearby the available holes, the next possibility is the so-called recombination. Right? So this is the process wherein as the free electrons from the n-type side diffuse through the p-n junction, the free electrons release energy. So since they are moving, they are consuming the kinetic energy. And as they release the energy, eventually they will recombine. They will lose the energy and will fall on the valence energy level and eventually recombine with holes in the p-type. So after the diffusion, the next possibility is the recombination. And after the recombination, we can notice that the free electrons already occupy the holes. So the free electrons already become valence electrons. So in this area, there are no longer, we don't have any free electron as well as any free holes. So this area within the p-n junction is what we refer as the depletion region. So after the diffusion, you'll have the possibility of recombination. And once recombination happens, we will form the depletion region. All right? So as the result of the recombination processes, the p-n junction area becomes depleted of charge carriers. So this area, the depletion region, does not have any free electron and holes. All right? But we don't have free electrons and holes, but we have positive ions as well as negative ions. And each pair of the ions is what we call dipoles. Within the depletion region, there are no charge carriers in the depletion region, but there are pairs of ions, or we call them dipoles, comprised of the negative acceptor ions in the p-type side and the positive donor ions in the n-type side. All right? Is it clear so far?
Yes po, sir.
All right, thank you. So because of these dipoles, internally inside the p-n junction, there we will have a built-in voltage. Nagkakaroon tayo ng internal voltage. Okay? Positive potential on the n-type side because of the positive ions and negative potential on the p-type side because of the negative ions. So by having dipoles, we have the internal or the built-in voltage or potential. Okay? So the dipoles produce the built-in potential across the p-n junction. So the transient movements of charge carriers continue until the PN junction reaches the equilibrium condition. Okay? So you have the diffusion, followed by recombination, followed by the formation of depletion, and inside the depletion you have dipoles, and as this continues, the built-in potential increases. All right? So the equilibrium happens, or that means the diffusion current will eventually become zero. The equilibrium happens, so the movement of carriers stop when the built-in voltage becomes equal to the so-called barrier potential. So the built-in potential increases up to a voltage value equal to the barrier potential. So when we say barrier potential, or before that, regarding the built-in potential, it can be calculated. So you can estimate or you can calculate how much is the built-in potential or in a PN junction. That depends on the acceptor concentration and on the donor concentration. So built-in potential is equal to KT over Q times the natural logarithm of the product of acceptor concentration and the donor concentration divided by the square of the intrinsic concentration of semiconductor. Okay? So VO is the built-in potential in PN junction. K is the Boltzmann constant equal to 1.38 times 10 to the negative 23 joules per Kelvin. T is the junction temperature in Kelvin. Q is the charge of carriers equal to 1.6 times negative 19 coulomb. Na is the P-type acceptor concentration in terms of per cubic centimeter. And Nd is the N-type donor concentration in terms of per cubic centimeter. And Ni is the intrinsic concentration in terms of per cubic centimeter. Okay? Now going back on the barrier potential. We said that we reach equilibrium when the built-in potential becomes equal to the barrier voltage or barrier potential. So barrier potential, this is the built-in potential across the PN junction that limits. All right? So pag sinabi mong barrier, it prevents, no? It prevents further movement. So that limits further diffusion of carriers unless we apply forward bias. Okay? So in this example, let's say you have holes wanting to diffuse across the N-type. So once we accumulated enough number of positive ions, the positive holes will eventually be repelled by the sufficient amount of positive dipoles. So pag nag-attempt yan, because of the enough positive charge, they will be repelled back to the P-type. Okay? So hole diffusion from P-type is prevented by the positive ions of the barrier potential in the N-type side. And likewise, the further diffusion of electrons from the N-type side will be repelled by the enough number of negative ions in the P-type side. Okay? Within the barrier voltage. Okay? So again, is this clear? Please confirm.
Yes po, sir. Clear po.
All right, thank you. Okay, so we continue. So for silicon material, the typical, so again, typical lang yan, hindi yan laging 700 millivolts. So the value of the barrier potential of silicon is around 700 millivolts. So later on, when we do problem solving, you will notice na pwedeng maging around 600 millivolts or sometimes pwedeng umakyat ng 800 millivolts. Okay? While for germanium semiconductors, the barrier potential is within the range or close to 300 millivolts. All right, so that ends our discussion on the PN junction in the equilibrium. So we can proceed with the PN junction under forward bias. Okay. So this is the PN junction under forward bias. So again, when you say forward bias or FB, this permits the flow of drift current through the PN junction. So under the equilibrium, since we do not have any voltage, electron flow uses the diffusion mechanism. While when we apply bias, it means we are applying voltage. So the movement of carriers will now depend on the drift current. Okay? So forward bias, the application of voltage permits the flow of drift current through the PN junction. So to apply forward bias, we apply positive voltage at the P-type side. So pakitandaan, positive voltage on the positive type, negative voltage on the negative type. Okay? So that will provide the forward bias. And another requirement, make sure that the applied bias voltage is larger than the barrier voltage. Okay? So those are the requirements to apply forward bias to semiconductor devices. All right, so the P-type is labeled as the anode terminal, while the N-type is denoted as the cathode or using the symbol letter K. Okay. So how the carriers flow in the PN junction under forward bias? So again, the anode is connected with the positive voltage of the bias, while the cathode or the N-type side is applied with the negative of the bias. Then internally, you have the barrier voltage. Again, you have positive on the N-type, negative on the P-type side. So when we apply positive voltage on the P-type, this positive voltage should be larger than the positive of the barrier voltage. All right, so yun ang requirement. The magnitude of the bias voltage must be larger than the internal barrier voltage, so that we can push, we can repel the positive holes pass through the positive barrier potential. So without the forward bias, the holes will be repelled by the positive of the barrier potential. But with the applied bias, since this is larger, it will have a more dominant effect on the carriers. So positive on the positive holes, it can repel, it can push forward the majority holes pass through the PN junction. So pwede silang magtuloy-tuloy dito. Okay, so eventually as it crosses the PN junction, the majority holes eventually will become minority holes. So holes pa rin sila, but since they are already in the N-type, minority na lang ang description natin. Okay? So is this clear so far? Please confirm.
Yes, sir.
Opo.
All right, thank you. And on the other side, we apply negative bias on the cathode, and the magnitude of this must be larger. So magnitude ang pinag-uusapan natin, no? The voltage of V bias must be larger compared with the barrier voltage. So when that happens, the negative V bias will repel the negative free electrons and effectively push the majority free electrons through the PN junction. So kumbaga negligible yung negative dito, no? So the majority of the free electrons can pass through the negative ions in the barrier potential. And eventually, they will become, so once they enter the P-type, the majority free electrons will become minority free electrons. All right, so a diode, we can say, allows at the same time the flow of holes as well as the flow of free electrons. So notice that hole flow is from anode going to the cathode, while free electron flow or simply electron flow is from the cathode going to the anode. Okay, napansin ba yon? Please confirm.
Sir, ano nga po ulit yan?
All right, yung hole flow.
Opo.
Hole flow is from anode going to the cathode. While electron flow in diode is from cathode going to the anode.
Okay po.
Okay, so sabay yun, pero magkaiba sila ng direction. Okay? So,
Basta po sir yung holes papunta dun sa N.
yes, or pwede natin palatandaan diyan, ang holes are positive. So they will be attracted towards the negative.
Okay po.
Or electrons are negative, so they will be attracted towards the positive. Okay, so yun na lang.
Okay sir.
Okay. So we can see that the majority holes as well as the majority free electrons are all flowing toward the PN junction. So lahat ng majority holes papunta ng PN junction. Majority free electrons are also flowing towards the PN junction. So in forward bias, the majority carriers flow toward the PN junction, while the minority carriers are moving away from the PN junction. So dito yung minority holes palabas ng PN junction. Likewise, minority free electrons are moving away from the PN junction. Okay? So dinescribe lang natin yung movements. And because of the presence of the carriers, the depletion region eventually disappears in forward bias. So again, depletion region is described as the area in the PN junction without any charge carriers. And when we apply forward bias, in the PN junction, we now have carriers. May free electrons, then we also have holes. So that means this area is no longer depleted. All right, so we can say that the width of the depletion region decreases in the PN junction. And also, importantly, in forward bias, remember that the resistance of PN junction lowers and permits the flow of current in forward bias condition. Okay? Then continuing on the resistance of PN junction under forward bias. So again, you have the majority holes, minority holes, majority free electrons, and minority free electrons. So the P-type or the anode has more positive voltage than the N-type cathode. So therefore, free electrons flow from cathode to anode, while holes move from anode to cathode. So this is the polarity for the forward bias voltage. No? Again, positive on the anode, negative on the cathode. And it will allow the forward current. All right? So normally, when we say forward current, we refer to the whole flow. So pag sinabi nating forward current, it is the flow of current from the anode going to the cathode. And it coincides with the flow of the holes. So forward current is the same direction with the whole flow, but of opposite direction, but equal magnitude with the free electron flow. All right, so is this clear? Please confirm.
Yes, sir.
Okay. Okay, next is we have the saturation current through the PN junction. So we have this equation. So saturation current equals A times Q times Ni squared multiplied by open close parenthesis d sub n over Na times Ln plus d sub p over Nd times Lp. So Is is the saturation current, typically in femtoamperes or 10 to the negative 15 amperes. A is the cross-section area of PN junction, typically in micrometer squared. Q is the charge of carriers, equal to 1.6 times 10 to the negative 19 coulomb. Ni is the intrinsic carrier concentration, typically in electrons per cubic centimeter. D sub n is the electron diffusion constant, typically in square centimeter per second. Dp is the whole diffusion constant in terms of cm square per second. Ln is the electron diffusion length, typically in micrometer. So kung gaano kalaki yung size ng semiconductor natin, no? While Lp is the whole diffusion length, typically also in micrometer. And Na is the acceptor concentration in per cubic centimeter, and Nd is the donor concentration in per cubic centimeter. So regarding the forward current, so balikan natin yung saturation current. So if you want a higher saturation current, so kita naman, no, you need larger area. What else? You'll be needing lower doping concentration, no? So kailangan mas mababa yung acceptor concentration, as well as you need a lower donor concentration to increase the saturation current. Okay? The rest are actually physical parameters or physical characteristics of semiconductors, no? So medyo wala tayong magawa dyan, no? So you have Q and I, D sub P, D sub N, D sub P. Those are characteristics, inherent characteristics of the semiconductors. So if you want to design a semiconductor device, you can control the size or the area, the acceptor and donor concentration, as well as the length, no? So you can design the semiconductor size. Now for the forward current through the PN junction, so this is the equation. So forward current is equal to the saturation current multiplied by the exponential of the forward voltage over the thermal voltage minus 1. Okay? So IF is the forward current in amperes, but typically this is just in milliamperes. IS is in saturation in amperes, typically in femtoamperes. VF is the forward voltage or bias in volts, typically in millivolts. VT is the thermal voltage, typically in millivolts. So we can calculate the thermal voltage using KT over Q. K is the Boltzmann constant. T is the junction temperature, the temperature inside the PN junction in Kelvin. And Q is the charge of carriers. All right, so based on this, if you want higher forward current, it requires higher saturation current or a larger forward voltage. So pag mas malaki, exponential yung effect niya, no? As you increase the forward voltage, it will result to exponential increase in the forward current. Okay? So are the equations clear so far?
Yes po, sir.
All right, thank you. So we continue with our slides. So again, continuing on the forward current, so I try to use the equation and plotted the forward current of a PN junction under forward bias versus the forward voltage. All right, so you have your forward current IF in milliamperes, and on the x-axis we have the forward voltage VF in millivolts. So we started from 600 millivolts going up to 950 millivolts. And at some point, we can notice the exponential increase in the forward current. Okay? So in this example, in this simulation, I set the temperature to room temperature equal to 300 Kelvin. So the thermal voltage is equal to the 25.88 millivolts. And then from there, we can calculate the built-in potential using this equation. So the built-in potential is 764.78 millivolts given the acceptor and donor concentrations. Okay, so we'll be able to compute for the built-in potential. So in this case, the built-in potential is around here. That is 764.78 millivolts. So that means above the built-in potential, the current will become more than zero. All right? Or above, when the bias voltage or when the forward voltage is larger than the built-in potential, we can say that the PN junction is already forward bias. So we expect a flow of the forward current. Okay, is that clear? Please confirm.
Yes, sir.
Po,
Yes.
sir.
Yes. Go ahead. All right, do you have question? Please go ahead. Question? Hello?
None po, sir.
Oh, none. So, okay. Thank you. So, I'll continue. And then from there, you can also get the saturation current. So, let's say these are the given parameters. We can calculate the saturation current equal to 17.73 attoamperes. So, take a snapshot and then try to calculate for yourselves. And let us see if we get the same answers, no? So para sure tayo na pero tayo ng style ng computations, okay? So given these parameters, we can now calculate the forward current. So you have the IS, you have the thermal voltage, and the forward voltage would be this one, from 600 to 950. Okay, so the built-in potential will indicate the boundary. So below this point, the PN junction is still not turned on. Above this value, the PN junction is forward biased or turned on. So we have here a sample measurement. So at a forward bias equal to 900 millivolts, the computed forward current is 22.62 milliamperes. So again, you can try using the equations and let us see if we get the same answers. All right, that ends our discussion on the forward bias. So let me continue the behavior of the PN junction under reverse bias. So when you say reverse bias, this is the condition that prevents drift current through the PN junction. So pag sinabi natin reverse bias, ito yung turned off. Naka-off yung device natin, no? So to apply reverse bias, the positive bias voltage will be connected to the negative type, while the negative voltage will be attached to the positive type material. And for the magnitude, the bias voltage must be I think baligtad ito, no? It should be less than. The bias voltage must be less than the so-called breakdown voltage. So we must avoid the breakdown condition. So again, let me correct this. The magnitude of the bias voltage must be less than the breakdown voltage. Okay? Or if we consider the sign, pwede rin to, no? The bias voltage must be more positive compared with the breakdown voltage. So since breakdown normally is a negative voltage. Okay? So para lang hindi magulo, just consider the magnitude. So the magnitude must be less than the magnitude of the breakdown limit. So under the reverse bias, again, these are the conditions. So here we have the correct version. No? Magnitude of the bias voltage is less than the breakdown limit. Then the negative potential attached to the p-type. The positive voltage connected on the n-type. And because of that, the majority carriers will drift or flow away from the p-n junction. Since you have negative voltage on the p-type, this negative potential will attract the positive holes. So the holes will move towards the negative. They will move away from the p-n junction. On the other side, since we apply positive voltage, this will attract the negative free electrons. So the free electrons on the n-type side will move towards that positive voltage, will move away from the p-n junction. Right? So is this clear?
Yes, sir.
All right. And because of that, we expect that the depletion region in the reverse bias will increase. So as the charge carriers move away from the p-n junction, the depletion region widens. So lalaki yung area without the charge carriers. And since the depletion region widens, the internal resistance of the p-n junction and the reverse bias also increases. So the internal resistance of reverse bias junction becomes very, very high. Okay? So the question is, when will the widening of the depletion region stop? It says here that the widening of the depletion region stops when the internal junction voltage eventually becomes equal with the applied bias voltage. All right? So when the internal voltage eventually equals with the bias voltage. So let's say you apply 10 volts at the outside. So the widening of the depletion region stops when the internal voltage becomes 10 volts. Okay? So the current along the p-n junction and the reverse bias is almost zero. And the leakage current consists of, we have the so-called saturation leakage current. These are thermally generated carriers in the p-n junction. And another type is the surface leakage current. These are the whole current flowing along the surface of the semiconductor. All right, so let me illustrate the saturation leakage current. So the reverse current due to the saturation leakage current is totally zero when the internal junction voltage equals the bias voltage. So for example, you have positive 10 volts on the outside terminal on the cathode. And you also have positive 10 volts on the internal junction, on the p-n junction. So the negative free electron will not be attracted to any of the two since they have the same amount of electronic force. So magkapero sila ng effect. So they will cancel each other. So that means the electrons will not move. Likewise, the holes will not move since you will have the same amount of negative potential. Okay, is that clear? Please confirm.
Yes po, sir.
All right, thank you. Now, what happens if there is a thermal generation? So you have the semiconductor device, and let's say the p-n junction, the temperature in the p-n junction increases. So by virtue of the generation process, when one of the valence electron absorbs thermal energy, that valence electron will become free electron. And as the free electron escapes the valence orbit, it will leave a vacant space. So that will produce hole. So the thermal generation will produce the free electron and hole pair. Now, when we have a free electron, the free electron will neutralize the positive ion. As well as the positive hole, it will neutralize the negative ion. So as a result of the thermal generation, the number of dipoles inside the depletion region decreases. So that would make the internal voltage reduce, okay, to a lower value compared to the applied voltage. Is that clear? Please confirm.
Yes, sir.
All right. And when this happens, you now have a higher voltage at the outside. So the free electrons will once again be attracted towards the positive 10. Since positive 10 will have higher effect compared with the positive 9.8. So eventually, the free electrons will move towards the cathode. And this movement is what forms the leakage current. Okay? Or specifically, that is what we call the saturation leakage current. Now, in electronics, when we say saturation, we describe the maximum condition. All right? So even though you apply higher reverse voltage, but the available carrier in the PN junction, let's say in this example, is only one. So the amount of free electron that can rotate or can leak through the circuit will only be limited to that one free electron. So even though you increase this to 20 volts, but since there is only one available free electron, the leakage current will only be equivalent to that available free electron. So that's why we call it saturation. So once you get the maximum current, hanggang dun lang, no? So if you want to increase the leakage current for whatever purpose, then you have to increase the temperature. So as you increase the PN junction temperature, you will be producing more number of free electrons. And once you have more available electrons, the leakage current will increase. Again, is that clear?
Yes, sir.
All right. Now, sir, what will be an example where we want the leakage current to increase? Diba? Normally, in general, leakage current is not desirable. We want the leakage current ideally to be zero. All right? So one example wherein we need leakage current, one example would be, let's say, if we will use the PN junction as a temperature sensor. So meron tayong mga thermal semiconductor sensor. So the mechanism of those thermal sensor is the reverse bias leakage current. So once you increase the temperature, it will generate leakage current, and the resulting leakage current through the circuit will increase. So increasing current corresponds to increasing temperature. So in that way, you're able to detect whether the temperature is increasing or decreasing. Okay, naintindihan ba?
Yes,
Yes,
sir.
sir.
Po, sir.
All right, sige. Thank you. So we continue. Sir, how about the surface leakage current? Regarding the surface leakage current, this is the flow of leakage current along the surface. So what is in the surface? Let's say you have here a silicon crystal. So we assume that every silicon atom within the silicon crystal, each of them will be completely filled. Each of the silicon atom will have a perfect 8 valence electrons, except for the silicon atoms around the surface. So ang assumption natin, ito yung pinaka-boundary. So therefore, we will no longer have silicon atoms dito sa side na to. So the atom on the corner will have only 2 neighboring silicon atoms. So that means you'll have 2 vacant spaces, or you'll have 2 holes. Along this surface, the silicon atom was able to covalently bond with 3 neighboring silicon atoms. The 4th neighboring atom is missing. Kasi yun na yung limit ng material, no? So that means we will have a vacant space. Naintindihan ba yung concept? All right, so along the surface of semiconductors, we can assume that all of those edges, there are existing holes along the surface of any semiconductor devices. Okay, is that clear?
Yes, sir.
All right. So if you draw a PN junction, so you have here holes, then along the edges or along the surface, you have holes, even on the N-type side. So along the surfaces or the edges, meron tayong holes. And the surface leakage current will be formed when one of the free electrons enter the surface holes. So once it reaches one of the holes, that electron can now move from one hole to another hole until it exits the semiconductor device. Naintindihan ba yon? Please confirm.
Yes po, sir.
All right, thank you. And then finally, we have here the PN junction under the breakdown limit or breakdown condition. So breakdown in PN junction happens when the electric field across the PN junction becomes extremely high. Electric field is defined by the voltage across the junction divided by the thickness of the depletion region. So based on this electric field equation, breakdown can happen when there is very high junction voltage or when there is very, very thin depletion region. So that provides the 2 types of breakdowns. The first one is the avalanche breakdown. This is the breakdown condition attributed to the very, very high junction voltage. So when you have high junction voltage, you have extreme electric field. So there is a possibility of breakdown. So we refer to that condition as the avalanche. Another type is the Zener breakdown. This is the breakdown due to the very thin depletion region. So when the depletion region, the thickness is very, very small, the electric field becomes very, very high. So there is a tendency of breakdown. So we call that breakdown as the Zener breakdown. So Zener is actually the name of the engineer who discovered the Zener phenomenon, yung breakdown phenomenon. All right. So any question or clarification? Any question? Clarifications? No more
Wala naman
questions?
po, sir.
Right. So if there are no more questions, we will end our lecture.